I'm going to start by backtracking just a little bit when we're looking at system operation and beta mode versus alpha mode. So what is beta mode versus alpha mode? That's kind of an important key point with turboprop propellers. What ground versus flight is kind of a rough estimate of it. Which one's which? Beta tends to be for ground operations, including reverse. So on landing, we would go into reverse. And then alpha tends to be more of your flight modes. That's when it's acting as a it gets into a mode where it starts to act more as like a propeller to maintain its max prop RPM. Okay. Just something on here I wanted to make sure, and I can't remember if I pointed this out or explained it fully. So this is that propeller, your main prop governor again. And remember, in alpha mode, the pilot valve, speeder springs, and fly weights, along with the propeller, speed selection lever, is going to be in charge of the blade angle, right? It's going to control blade angle to essentially maintain max RPM, or a max of in this case 2200 RPM, but it could depend on different aircraft. So, but it'll maintain max prop RPM. Below that, when you're in beta mode, you have the beta control valve, and on this setup, the where you have an external pitch feedback mechanism, so around the outside, on the outside of the propeller, that external mechanism is going to feed back into the beta control valve. So your throttle, and then that feedback mechanism is going to control the beta control valve. So when this is in beta mode, just one thing I wanted to point out, and I couldn't remember if I did it. What's going to be going on with the fly weight and the speeder spring anytime we're in beta mode? You're going to be in an underspeed condition, right? Those fly weights are going to be tipped in, and they're going to be dropping the pilot valve down. And so that's essentially how this gets taken out of operation. That's essentially how the pilot valve gets taken out of operation, is when this drops down. Here's our oil on the far left here, oil dumped to, sorry, not quite the far left, the oil that goes to the propeller here. That when this pilot valve is down, that directly ports the output of the beta valve, the two outputs. There's one here and one here. One at the side of the beta valve, one at the end of the beta valve. That directly ports those to the prop. Okay? And so that's how it takes the propeller governor out of the equation when it's in beta mode. So oil will flow. Let me get my pen here. So the ports here will be open. The beta valve, or the pilot valve, will be dropped down. And so that directly ports oil. So the oil pressure comes in, and then the beta control valve can either route it through here to the prop, or it can drain pressure off. It can route pressure two different directions, through here and out to the prop. Okay? And then when that beta valve closes off, it allows oil to kind of flow back and out to the reduction gearbox. And so that's how it's taking the prop governor out of operation at those lower speeds. And I was afraid I didn't quite kind of explain very well how that operates. Let me get back to my. Now, if we skip ahead to the end, and I'm trying to turn off my pointer here. There we go. So where we left off is, here's our arrows, our overspeed governor. Where we left off was this whole system kind of put together here. And so where we can see our main prop governor with the beta control valve, does most of our normal operation. And then having our overspeed governor, that's kind of a backup that can dump oil, that can relieve pressure in this line if there's an overspeed condition, and that removes any oil pressure from inside the dome here, which allows the blades to go to feather. So operation very similar, just has a few more safeties and a few more items that help to control the engine. And then don't forget too that these engines often have a second governor for the power turbine, a power turbine governor. That isn't shown here. It doesn't deal with the prop oil system directly. But if it senses the power turbine spinning too fast, whether because the prop gets into an overspeed condition or for some reason you lose that link between the power turbine and the propeller, where the power turbine then can run away, that will reduce the fuel. That sends a command to the fuel control for the gas generator to reduce the amount of fuel going. Okay. So today, I'm just going to kind of wrap up by talking about installation, adjustment, and then operation when we run the aircraft. So most of these, almost all of these, what you'll see are going to be a flange shaft or a flanged shaft installation. And the reason for that is that tends to be the easiest way to have that oil port, the ability for oil to flow to and from the engine. The other reason is that this same propeller, remember this design, this is a Hartzell propeller. It's HC-B3TN, something like that. The Hartzell design is actually very similar to your other manufacturers. No one's got a particularly innovative propeller hub, so to speak. Really, the innovation they tend to have is in blade design and that kind of thing. But the reason it has this flange shaft is the other part of it is when we get into the TP331 and this same propeller on a different engine, is it allows for internal pitch change mechanisms and feedback mechanisms rather than the external. It's something called a beta tube. And we'll look at that when we do the TP331. So you're going to have maintenance manual. This kind of goes back to when Jeremy and I talk about it. You're going to follow the maintenance manual. There's going to be specific procedures for rigging it. Rigging is kind of is an art as much as it is a science or a skill. Sometimes some of these engines can be a little tricky because you're going to be rigging the engine, the fuel control. You're going to be rigging your prop governor. You're going to be rigging the propeller feedback mechanism itself. And when you're doing this, there's going to be a set order, a very specific order that you have to do it in. And I think that's the biggest takeaway on it is if you start having problems with something like this, people start chasing their tail by trying to adjust this or trying to adjust that or really the process to rig one of these turbine engines and to rig the propellers, the constant speed propellers that are on it, you really want to start at step one and work your way through. And maybe steps 1, 2, 3, 4, 5, maybe you're just verifying that things are correct. Okay. But if any of that's out of adjustment and you start on like step 5 and 6 making some changes, and then you go back and say, oh wait, there was something not an adjustment in step 1 or 2, you're going to have to go back through the whole thing anyways, and you're going to end up, like I said, chasing your tail. So, but with the flange shaft installation, just a few points on those. There can be a couple different ways they can be installed on the flange shaft. Some of them use, in fact, I've had on the same airplane where there were different versions of the same prop. So the engine itself has a flange with holes in it. That's pretty much universal, right? And the two ways they can be installed on there is you're going to, the prop's going to mate up to that flange. There's typically going to be an O-ring that goes underneath there because you've got the oil passage running through the center of the shaft and the center of the dome, or the center of the back side of the hub. But some of them, there might be bolts that go in. There are threaded bosses in the prop hub where you run bolts from the back and tighten them through the back of the flange and into the prop hub. Some of them, the prop hub has studs, threaded studs that go through the holes on the flange, and then you use nuts on the back side of it. And typically, if they're bolts, the bolts are not, the bolts are a free threaded bolt. They're not a Loctite bolt. So after they're installed, they have to be torqued, and then they have to be safety wired. If you have the studs that slide through and then nuts go on the back, those are almost always a lock nut of some kind. They're self-locking. My experience was I preferred the bolts with the safety wire over the lock nuts. And the reason for that is it's a difficult area to get to. It's actually easier to put the bolts in where you can spin them all the way down by hand and then just do a final torque on them than the lock nuts where you have to sit there and wrench them all the way down by hand when there's like 12 to 16 lock nuts on there. And these are big. They're like 3/4. You need like a 3/4 to 1 inch wrench in order to do it, depending on the prop. So my clicker doesn't want to work. So when they're on, when we operate this, most of these, if you have a free power turbine, are going to have 3 controls. Majority of them do. Although the Saab 340s I worked on were a free power turbine, they only had 2 controls. They had a power and a condition lever. They didn't have a separate prop lever. But you're going to have a power lever. That's kind of your throttle, like what you have on a on a recip aircraft. That is right now it's shown in the idle position. Okay. And it's these first set of levers on the left here. It's shown in the idle position. Pushing it forward from there is going to increase power, and it increases power. That's directly controlling the amount of fuel going into the gas generator. Okay. The idle position it's against the stop. If you look on here, there's a kind of a white box at the back edge of these. That's your ground idle stop. Anything behind there is getting into a reversing mode. But there's always something that prevents them from just being pulled back into reverse accidentally. In the case of the King Air shown here, you have to physically grab the knobs and you have to lift them up. And then you can start pulling the levers back into reverse. And what's going to happen is as you pull back, when you first start to bring it back, it moves those blades they're in beta mode. It starts to move them to a very, very fine pitch and then ultimately starts to reverse the direction. And once the blades are in a reverse direction, start to go in a reverse direction, as you continue to pull back, it actually starts to throttle the engine up. It does the same thing as if you'd push the levers forward. It starts to add more fuel to the fuel control. And just like beta range in forward, just like thrust beta range, the blade angle, the reverse blade angle, and the power are both controlled by those thrust levers when they're in reverse. Okay, behind that gate. The other style I've seen is instead of physically lifting up on the levers, physically lifting up on the knobs, there's some kind of a trigger that you grab with your pointer fingers or your middle fingers underneath the knobs. So you have to lift that trigger up and then pull back on them. Once they're behind that gate, though, you don't have to keep lifting. You don't have to keep pulling the trigger. Once you've gotten it behind the gate, then you can just operate them like normal. And then when you bring them back forward, as you come in front of the idle mark, they will either snap back down so that you can't accidentally pull them back again, or the trigger will release. You'd have to pull the trigger again to bring them back. Okay. The propeller lever there, they're currently in a feathered position. All the way back is feathered. And you can't see it very well in this diagram, but it's got kind of directly below the levers here, there's kind of a crosshatch pattern on the throttle quadrant there. And that's a common indicator of the feather range. And so when they're pulled all the way back like that, it feathers. As you push them forward, they go into a higher RPM. So to bring the blades out of feather, you push them forward just a little bit. And then again, remember in beta mode, so low speed ground operations, reverse, any of that, it doesn't matter where you put those propeller levers, as long as they're not in the feathered position. If they're anywhere between low and high RPM, they're not going to change the blades because the blades are in that underspeed condition at any lever setting. And right now, and the beta, the beta valve is controlling it, which is connected to the throttle, the power levers rather than the prop levers. Okay. But what you normally do is push them all the way forward into the high RPM position. And that's where they would say until you get into the alpha range, And then once the engines are in alpha range, if you do want to control the pitch, if you do want to control the prop speed, the blade pitch and prop speed, then you can adjust the propeller levers. But that'll only take place if the what's called the condition levers, we'll get to in a minute, are in above the flight idle or at the flight idle position, and then the power levers are up above idle as well. And at that point, then those prop levers start to function like a typical constant speed propeller prop lever. But pushing forward increases RPM, pulling it back decreases RPM when it is in alpha mode. When you have enough power being developed by the engine that it switches over to alpha mode. As long as it's in beta mode, it will not do much other than it can put the propellers into feather or take the propellers out of feather. The third lever there is the condition lever, and this is the pair on the right. And so the way you can see these are arranged is, you know, the power levers, you got the left engine and the right engine power lever, they're grouped together. And then the prop levers, left and right engine together, and then the condition levers, left and right engine are together. And the reason for that is when you're making an adjustment, you tend to make the adjustment on both engines simultaneously. And so you group them by adjustment type rather than by engine. So the condition levers, they're currently in the fuel cutoff location. They're all the way back. These have basically three positions. As you come forward, there's a little notch here that's called low idle. That's your ground idle position. So for ground operations, that locks the propellers into beta mode. You cannot go into alpha mode when they're in the low idle position like that. And then when you push them forward, all the way forward up here is high idle, and it's still in beta mode at that point until you start to bring your throttles forward, until you bring your power levers forward. And you'll hear me say throttle, power lever interchangeably. They're basically the same thing. And so you really don't ever operate the condition levers anywhere between a low and a high idle position. You're in one or the other. If you're on the ground and you're taxiing, you're going to be in low idle right in this area. And you can see what happens with these. They come up and they kind of snap in. There's a little hook there. So it's the same kind of a thing. Once those are once they're out of the fuel cutoff position, once they're in the low idle position, you can push them forward, you can pull them back. But when you pull back on them, you won't accidentally drop down into cutoff, right? You don't want to accidentally shut your engine off. So there's a little hook where you have to grab the lever and kind of move it to the outside and then pull back to get it down into that cutoff position. You almost kind of got to go in an L pattern. And again, that's so you don't accidentally cut fuel off to your engine. Okay. So under normal operation, when we are starting the engine, we would have our power levers in idle. Our condition levers, they're in feather for shutdown. We actually put them back to the high RPM for starting, although the propellers, the blades will not change angle until there's oil pressure, until the engines have actually started. And then the condition levers stay in fuel cutoff while you start motoring the engine, you get the engine spinning, and when you're ready to introduce fuel, when you move these from fuel cutoff to the low idle position, that's what opens the fuel valve inside the fuel control and actually sends fuel to the nozzles. Okay. From an indication standpoint, you see something that looks like this, and this is an older setup. So our King Air is older. I hate this gauge setup. And the reason I hate it is that it is not intuitive at all. Okay. Well, the new ones have the same number of dials, or if it's on a screen, it's the same indications. But here's what the difference is. I'll draw it as we go. So this one, the top left, you have pairs of dials, and they're arranged as left engine, right engine. So the top left dials, the ones that are labeled E there, top left here, there's a left engine ITT and a right engine ITT. It's interturbine temperature. Okay. Temperature is pretty important. We want to know how hot our engine is. Okay. Below that is our gas generator speed. Left engine, right engine. And that's going to percent RPM. Typically, you're running somewhere between 0 and 100%. Typically, idle's around 50%. It may go up to 104, 105%. Sometimes there is an authorization for a certain amount of overspeed if necessary. The next gauges, labeled D here, are torque. Again, left engine, right engine. And below those are propeller RPM. Left propeller RPM, right propeller RPM. Okay. As you continue along, you also have things like fuel pressure, left and right engine. Fuel flow, left and right engine. Fuel pressures in PSI, fuel flows pounds per hour. Oil pressure, left and right. And oil temperature, left and right. What do you see? What's kind of a pain about that? What if I want to look at how my left engine is doing? What do I have to do? I have to go here, and then I have to skip one to here, and I have to skip one to here, I have to skip one. Newer versions of this, what you're going to see is a vertical arrangement. Okay? Your most important gauges are at the top. And typically, most important are actually going to be torque is our power setting. So typically, you would have torque. Here's our left engine and our right engine. And then below that, you would often have your gas gen, RPM, what I call RPM sub G, RPM for the gas generator. Below that, RPM for the prop. Below that, we would have, did I have ITT yet? Here's ITT, right? And so on. So they would be a vertical. So if I want to know what the left engine's doing, all I got to do is shoot down this left column or shoot down the right. That's what you see on more modern aircraft. This isn't a very intuitive one, but you can see what is monitored here. And the big thing with prop, so our gas generator is very high RPM. This one's listed in percent, up to 100%. 100%, I want to say somewhere around 30,000 RPM. The prop RPM is almost always given in actual RPM, rotations per minute. Because in this case, it maxes out at 2,200. So when we run these, you're going to be, when you get out into the field and you're going to be operating aircraft as part of your job, you're going to need to run these. And so it's important to kind of be able to understand, before you start running, how are your gauges arranged? What are they telling you? How do I interpret it? And what do I need to keep an eye on while I'm going, right? What are some things we need to keep an eye on? We're testing these with maintenance. Sometimes we're pushing these engines to their max. What are some things you would want to keep an eye on during the process? So torque. Torque is the power setting. You can tear a turboprop engine apart or destroy a propeller if you over torque it. If you jam your throttles forward and you pull back on your prop RPM and you're in the alpha range, you are going to over torque the engine. Kind of a rule of thumb we always had is the prop levers have to stay in front of the power levers. You never swap them unless you are specifically trying to max out your torque. Okay? What else? What other things do we have to worry about, especially with propellers? Torque's the only thing we can max out. RPM, prop RPM is a big one, okay? Same deal. You've got that at high RPM and you jam those throttles forward. You may actually overspeed it before the prop governor or the overspeed governor or the power turbine governor is able to take that into account. Okay, these are mechanical systems with feedback. They take some time to react. So you want to make sure that you're paying attention so you don't damage anything in the process. Okay. So when we're running these, the start sequence on a turboprop, a free power turboprop, is interesting in that we shut down the aircraft. It's going to be in feather, right? Those propeller blades want to go to feather. These are designed to go to feather when you lose oil pressure. We start the engine in feather because we don't have to worry about that load because the free power turbine isn't connected directly to our starter. But we do want it to come out of feather fairly quickly. We want to verify that there's oil pressure, and we don't want to be putting all that extra load on the engine for a long period of time. Although most of these, like the PT6, you can run it in feather all day long if you want. It'll sit there just idling along. You don't want to pull power, you'll over torque the engine. But you can idle in feather all day long if you want. Your cabin will stink like exhaust, but you know. So when we're running these, what we're going to do, the first thing we do is we turn on our starter first. We get the engine rotating, and you'll get rotation. Now here's an interesting thing. You'll see this on newer aircraft. They'll say oil pressure climbing. Usually you can get oil pressure before you fully start the engine. However, on some older turboprops, like the one we have, you cannot run the oil pressure gauges. They run on alternating current using an inverter, and you will destroy the inverter if you're trying to run it while you have these big electrical loads going to the starters. And so you may not have oil pressure. In fact, starting our King Air, you don't have an oil pressure reading. Once you get your engine rotating, then you're going to move the condition lever to the idle position. And what did I say? What does the condition lever do? When we move it to the low idle position, what is that going to do? It's on the slide. That's going to introduce fuel. We take it out of the fuel cutoff position and move it to a low RPM. So that it works as it controls the prop RPM. It controls whether you're doing a low or a high idle, but it's also going to control whether there's fuel going to the engine or not. So ignition and fuel, the engine lights off. We get ITT rise. And your prop, you'll see the prop will start turning here, but the only reason, why would the prop start turning before we've got it going? When we engage the starter isn't connected to our propeller in any way. Why would we start to get some rotation? What's going on? If the starter is not hooked to our propeller, why does it start to spin? What are we starting to get happening when we engage the starter? We're starting to move the gas generator. What's the gas generator made up of? What makes up the gas generator? So you got a compressor and a turbine, the turbine that drives the compressor. So you're going to get airflow through the engine. And it's that airflow through the engine hitting the free power turbine that's going to start rotating it. In fact, you can go out, if you know you have a free power turbine, you can hold the prop still while the starter is engaged. You'll feel a little bit, but not much. Okay. We would do it to do like compressor washes. We would shoot water into the inlet to clean the inside of the engine. We'd stand there and hold the prop. Now, you don't want to try to hold it when the engine lights off. So you make darn sure that your igniter circuit breakers are pulled. You make absolutely sure that that fuel cutoff lever stays in the cutoff position, right? But you can hold it there. If you try to do that with a fixed shaft turboprop, has anyone seen what the starter generators on these things look like, how big they are? They're about 8 inches in diameter. It's an electric motor. They weigh about 40 to 60 pounds. And if you try to hold on to a fixed shaft turboprop, when you kick the starter in, it's going to send you flying across the hangar. It's a big electric motor with a giant gear reduction on it. It's not going to care that you're holding it. It's going to try to tear your arms out of your body. So you need to know that if you're paying attention. So engine starting off, if light off doesn't occur, we want to abort our start. Once the engine's up and running, condition lever is at low idle. We're going to get up to 50% and start ignition switch off. Okay. If we look at what an actual checklist looks like, it looks something like this. And I'm going to just change the way our screen works real quick. Mm-hmm. Duplicate. So here is an example of a run checklist. We don't need this thing here. So it starts out with pre-run. We do a walk around before we run one of these. The left side here. More pre-run. Okay. Before start, we make sure everything is secure. Some of the things we do, we want to set our lever positions. So our power levers, we want to make sure they're in idle. They're not in a high RPM. They're not in a reverse condition, anything like that. Prop levers, we actually move them to a high RPM condition. And the condition levers are in cutoff. Okay. We turn on things like boost pumps and whatnot. But when we start, there's clearance and that kind of thing we have to obtain down here. Oops, went too far. But then the start switch comes on. We want to get our engine at what's called max motor. So we let it motor as fast as it can. And the prop will start to turn here, but it's not going to be turning very fast. Again, because it's just the air being pulled through the engine at about 12%, 12 to 20% gas generator speed. That's going to do it. And we'll have our igniters come on. We move our condition lever to low idle and monitor ITT as well as our gas generator speed. We can also monitor our prop speed, make sure our prop does start to increase. We want to make sure it's not that we don't have a bad gearbox, or there is a possibility in winter that these things can have ice issues, like you can get ice buildup between the spinner, what do you think, between the spinner backplate, the slip rings, and the like brush blocks and that kind of thing, if you get really bad icing in there. The engine will idle and stabilize at 50% NG. We disengage our starter. And then in the case of older aircraft, the oil pressure check is that our prop will come out of feather because we've set it to a high RPM condition. So as that engine oil pressure builds, that's another way to verify that you have oil pressure, is once the engine starts pumping oil into the propeller dome and brings it out of feather. Once it's out of feather, then we can go to various idle conditions. Here we go to a high idle condition to get extra power out of the generator for starting the other engine and whatnot. Okay. There's various checks in here, but the other thing I want to do is shut down. So when you shut down an engine, you always make sure that your props are in high RPM. Your condition levers you want in low idle. You want the engine working as little as possible. You want as little stress on the propeller as possible. Power levers, you make sure they're in idle, again, for the same reason. And then what we'll do is, in the case of this engine, we feather it, feather each prop. And then once the propellers have gone, the blades have gone into feather, then we can move the condition levers to cut off. Okay. And we essentially just cut off fuel to the engine to shut it down. Okay. So it shuts down in that feathered position, and it'll remain feathered until the next time you start the engine. And this will contrast with the TP331 or other fixed shaft engines where they have fine pitch locks to prevent the blades from going to feather on shutdown in order to minimize that load on the starter. So that kind of covers the PT6 and free power turbine turboprops. And next time we'll talk about the TP331, a fixed shaft turboprop. That also will include talking about something called a beta tube. When we talk about beta tubes, those aren't unique, however, to a fixed shaft turboprop. There are free power turboprop aircraft that use the beta tube. It's essentially an internal pitch change and feedback mechanism rather than the external one that's used on some aircraft.